Let us see another application of the gradient vector and the directional derivative. So we are told that a hiker climbs a hill whose shape is given by the equation z equals to 1000 minus 0.005 times x to the square minus 0.01 times y to the square, where x, y, and z are measured in meters and the hiker is standing at a point with coordinates 60, 40, and 966. The positive x-axis points east and the positive y-axis points north, which if we make a simple sketch here, so this is the x-axis and this is the east direction, and this is the y-axis and this is the north direction. So one of the vectors that can represent the east direction will be the vector with components. So east direction can be represented by a vector with components 1, 0, and then the north direction can be represented, one of the vectors that can represent the north direction will be the vector with components 0, 1. These are just two of the vectors that we can use to represent these directions, but there are many, many different vectors. And we are asked that if the hiker walks due south, will they ascend or descend? So due south means that one vector that can represent that due south, and let's sketch that here. So this is south. One of the vectors that can represent the due south is the vector with components 0 and -1. So a vector that can represent that, that direction is the vector 0, -1, but there are many, many different options for vectors. So we want to calculate the directional derivative in the direction of 0, -1. And for that, we'll have the directional derivative of z in the direction of u at the point 60, 40. So u in this case is this unit vector with component 0, -1. And that would be equal to the gradient vector of z at the point 60, 40, dot product the unit vector u, that unit vector with component 0, -1. Let's first find what is the tangent vector of z at the point 60, 40. So that would be equal to the vector with components, the partial derivatives of z with respect to x and y. So the partial derivative of z with respect to x is equal from here. Since these two terms are constants with respect to x, we only need the partial derivative of the -0.005 times x to the square with respect to x, which gives us -0.01 times x. And then we have the partial derivative of z with respect to y. So now these two terms are constant, so their derivative will be 0, and we only need to differentiate the -0.01 y to the square with respect to y. So that will give us -0.02 times y. And we need to evaluate that at the point 60, 40. So that gives us -0.01 times 60, comma, -0.02 times 40. So that gives us the gradient vector that has components -0.6, comma, -0.8. And now to find the directional derivative, duz at 60, 40, we need the gradient vector that we just found of z at 60, 40, dot product, the unit vector u with components 0, -1. So we'll have negative 0.6, comma, negative 0.x for the tangent vector, dot product, the unit vector 0, comma, -1. So that gives us negative 0.6 times 0, and then plus negative 0.8 times -1. So that gives us 0.8. So the directional derivative of z in the direction of u at the point 60, 40 is equal to 0.8. And that quantity 0.8 is a positive quantity. And that means that if the hiker walks due south from the point 60, 40, the hiker will ascend, so the hiker will ascend, and the rate of ascent of the hiker would be 0.8 vertical meters per horizontal meter. So since the directional derivative is positive, the hiker will ascend, and they will ascend by 0.8 vertical meters per horizontal meter. Let's see another, what happens if the hiker walks in a different direction. So now we are told that the hiker walks northwest. So northwest, again, with a simple sketch. Will be this direction. And we have northwest. And one of the vectors that can represent this direction is the vector -1, 1. One of the vectors that we can use. And since this is not a unit vector, we can find the unit vector that points at the same direction. So the unit vector would be equal to the vector -1, 1 divided by the magnitude of the vector -1, 1. So that would be the vector with components -1 over square root of 2 and 1 over square root of 2. Now from before, we know that the gradient vector of z at the point 60, 40, since this is the point that the hiker is standing, is equal to the vector with components -0.6 and -0.8. This is something that we calculated in the first question. Therefore, the directional derivative of z in the direction of u at the point 60, 40 will now be given by the gradient vector of z at the point 60, 40, dot product, the new unit vector that we just found, so this unit vector over here, which has components -1 over square root of 2 and 1 over square root of 2. So that would be equal to -0.6, -0.8, dot product, the unit vector -1 point square root of 2, 1 over square root of 2. So that would be 0.6 over square root of 2 minus 0.8 over square root of 2. So that gives us -0.2 over square root of 2. So the directional derivative of z in the direction of the unit vector u at the point 60, 40 would be equal to -0.2 over square root of 2. And this is approximately equal to -0.14. and that is a negative quantity. And therefore, now the hiker will descend. So the hiker will now descend. Since the directional derivative is negative, so that means that a hiker will descend at a rate of 0.14 vertical meters per horizontal meter. So since the directional derivative is negative, that means that the hiker will descend by 0.14 vertical meters per horizontal meter.